Hello everybody. In this section, we're going to talk about higher order partial derivatives. In the last section, we introduced partial derivatives. So we recall, given a function of two variables, then we can talk about partial derivatives with respect to x. We can talk about partial derivatives with respect to y. And both are called first order partial derivatives. In other words, if I talk about computing first order partial derivatives, you are going to derive two formulas. One is partial x, one is with respect to y. Now, if we repeat this procedure on top of these two functions, first order derivatives, then we can get second order derivatives. So repeating, we can get second order, and then we can generalize in theory to any order partial derivatives. So this part is partially from section 14.3. So second order partial derivatives. So if we're given a function of xy and take the derivative twice, when we say twice, it could be in different orders, but as long as you take the derivative twice, then we call that the result as second order derivatives. So we may have four different types of second order derivatives. For example, this symbol or equivalent to this symbol means you take the derivatives of, so we can look at this for the interpretation. So if we look at this, partial x squared, this means we first take the derivative with respect to x, and then we get a formula which is first order derivative. And then on top of this, we do another derivative with respect to x. So x. If we look at this symbol, then we have partial y, partial x, which means you take partial y first and then partial x second. Also, this symbol means take the partial derivative with respect to y twice. So if we arrange different orders of the second order derivatives, then we may have four different results, four different types of the second order derivatives. Now we look at a function given by x cosine y plus y e to the x. Find the second order derivatives, which implies you want to derive four functions corresponding to partial x squared, partial y squared, partial x, partial y. For this problem, I'm going to work on this first and then this first and next. And I'm going to leave the other two as your own exercise. You can try this after the lecture for your practice. So first, I'm going to look at partial square of f, partial y, partial x, which means we can rewrite this as partial y and partial f, partial x. When we write this, it means first take the partial derivative with respect to x, and then we take partial derivative with respect to y. So we split it into two steps. I compute inside the parentheses first. So that means y is frozen variable, or cosine y is just constant. So x times cosine y, then when you take the derivative with respect to x, it's just coefficient. And for y ex, y is constant. And e to the x derivative is e to the x itself. So y e to the x. So in other words, if I put this inside here, then I can have, by replacing simply, cosine y plus y to the e to the x. And then that becomes taking derivative with respect to y to this function. And in this function, y is variable, running variable, it's changing, but x is constant. So in other words, e to the constant is another constant. So you can think of this as a coefficient of y. So when we take the derivative, cosine y derivative is negative sine y. And y times constant, its derivative is its constant, its coefficient. So this is the answer. Now we look at the last one, partial f, partial x, partial y. So when I look at partial square f, partial x, partial y, we can rewrite this as partial x, and in the parentheses we write partial f, partial y. Which means I need to look at this first, partial f, partial y. So if we first look at partial f, partial y, I'm going to see this function. So here x is frozen. It's a coefficient, cosine y. Cosine y derivative with respect to y is negative sine y. So constant times negative sine y. So I put negative sine first. Plus, again, y times e to the x. E to the x is constant. Its coefficient. And y derivative is 1. So y times e to the x, its derivative with respect to y is e to the x. So I'm giving this formula into the parentheses. So partial x, negative x sine y plus e to the x. All right. Next, we take the derivative. We take the derivative inside the parentheses, but with respect to x. So sine y is constant. Negative x derivative is negative 1. So negative constant, negative sine y. And e to the x, because we take derivative with respect to x, so e to the x, its derivative is itself. So the answer is negative sine y plus e to the x, which is the same as here. So what we computed is partial square f, partial y, partial x. So the partial derivative with respect to partial y, partial x, and the second one is partial x, partial y. We switch the order, and the results are the same. And this is not accidental, so that gives us next mixed derivative theorem, or Clairaut's theorem. If there's a multivariable function, its partial derivatives exist. So first of all, computable, are nicely given. Then the partial x y is the same thing as partial y x. So it doesn't matter which order you compute. Sometimes this one is easier, sometimes the other reverse order is easier, but at the end you should come up with the same formula. And this page says partial derivatives of still higher order. So we can generalize first order partial derivative into second order. Then by repeating once more, we get third order, fourth order. So for example, this symbol means we take partial derivative of f with respect to partial x, partial y twice. So basically it means you can look at partial x and partial y, partial y, f. This is the same thing. And for simplicity, you don't have to every time write this parentheses. So I'm going to clear this, and there's no confusion. So that means you first take the partial derivative with respect to y, then again partial y, and then partial x. Of course, by Clairaut's theorem, it implies this is supposed to be the same as mixing its order. So you can do partial y last and second last, and the first one is partial f partial y. For the fourth order, the same thing. Partial x squared, partial y squared means do derivatives on partial x twice and partial y twice. This is fourth order. This is third order. So here's one example for fourth order derivatives. Computing this in general for function, just arbitrary function, it's really time consuming, but for this problem it is supposed to be easier. So for this, it's up to you which order you want to follow, but what I'm going to do is so if we look at the subscript, it tells you take the partial z, then partial y, then partial x, partial y. But by Clairaut's theorem, you can do in any order. So what I'm going to do is partial y twice and then partial x, partial z. So what I do is I'm going to rewrite this. I do partial y first, and then the second order, I do partial y again, and then partial f, partial x. And no, we don't have to write partial f again. So this is partial, and partial z. So we first do this thing with respect to y, which means one derivative, constant derivative is 0. And here this is 2xz are constant. Y squared derivative is 2y. So I'm going to copy everything in front of the parentheses, and inside is negative 2xz. This is coefficient of this term, and y squared derivative is 2y, and x squared y. This is coefficient. Y derivative is 1, so it's basically x squared. Now, next job is to take derivative of y with respect to y in this term. But the second term, the last term, has nothing to do with y. It's x squared, which means x is frozen or constant. Constant prime is 0. So for this, everything in before y has nothing to do y. So you can just copy that as coefficient. And y derivative is 1. So taking derivative with respect to y, it simply gives me negative 4xz. Now, the next thing is take derivative with respect to x. And the negative 4z's are constant, so it becomes negative 4z, x derivative, which is 1. And then there's only a single variable, and take the derivative with respect to z, which is negative 4. By Clairaut's theorem, or mixed derivative theorem, you are able to compute negative 4 by changing the order of derivatives. All right. At last, we are going to look over some important theorems which will not be which will be presented here, but we're not going to prove that in this course, and those proofs are going to analysis. So a function z equals f of xy, two-variable function, is differentiable at certain point x0, y0 if partial derivatives with respect to x and y exist. And the difference, delta z means, delta stands for change in value, which is basically this difference. So you can think of the plane, right? So suppose this is your target point, x0, y0, and you move a little bit to, in x coordinate we take delta x, and y coordinate we take so we take one step away from the limit. So this delta y means, so delta x means how much step size you move in x direction, and this is change in y direction. So if you change just tiny bit, one step, then the function value will change. Then the difference between these two function value will be delta z. So delta z can be written as partial derivative fx, partial derivative with respect to x times delta x, and partial y delta y, and plus epsilon 1 delta x plus epsilon 2 delta y. And where you can epsilon 1 and epsilon 2s are very small, in the sense that epsilon 2 goes to 0 when the step size are very small. And we call f is differentiable if it is differentiable at every point in its domain, and say that its graph is smooth surface. So typically when we think of this kind of problem, we are not really, typically, so we're looking at the, imagine a mountain surface, and when you move from one point to the other point, small enough, then their change can be approximated by this quantity, because if this is differentiable, these terms are very small. So this can be used for estimation purposes. And another one is, if the partial derivative fx, fy are continuous throughout the open region R, then f is differentiable at every point of R. And the last one is a little bit important. So differentiability implies continuity. So if f is differentiable, then f is also continuous, but not the other direction. All right, we're going to stop here.